Yeah, so welcome everyone to this very first seminar in the Quantum Gravity Across Approaches seminar series with the topic on observables. And just to say a few words from the organizers, Aaron Held, Lisa Glaser, Sebastian Fischetti, and myself. What is our intent for this meeting? So we all know that there exist various different approaches to quantum gravity that are all built on very different principles, assumptions, and also foundations. And that can make it often difficult for us to communicate and understand each other. And we think it's important that we meet on a more regular basis and tell each other what we are doing and why we think it's interesting what we are doing. And yeah, just to learn firsthand, but also that we might realize that there are some questions which are difficult for some approaches to answer, which are difficult for others. So we might learn from one another and maybe tackle the same problem from various perspectives. And with the seminar series, we want to foster the exchange across approaches and maybe give us new ideas, and maybe it will also lead to new collaborations. And the very first topic for our seminar series is the topic of observables, or one should say the lack thereof in quantum gravity. And we want to provide different perspectives on this question in the seminar series. And it is my great pleasure that we have Philipp Höhn today to give us an overview talk, or the first talk of this seminar series. And let me give a brief introduction about Philipp. So in 2008, he received his diploma, which is a German master equivalent at the Humboldt University of Berlin, and then moved on to do his PhD at Utrecht University under the supervision of Renate Loll. But during that time, he also worked with Bianca Dittrich on a canonical formulation of discrete gravity and Martin Boyowald on relational dynamics and effective approach to the problem of time. After that, he did a 3-year postdoc at the Perimeter Institute in Waterloo, where he explored the direction of going into quantum information and quantum foundations, for example, to think about reconstruction of quantum theory and how to obtain symmetries from quantum communication. He received a Marie Curie Fellowship to go to the Institute for Quantum Optics and Quantum Information in Vienna, and, for example, think about how to switch between quantum reference frames and switching relational clocks. And then from 2019 to 2020, he was a research fellow at the University College of London. And right now he is honorary associate professor at University College London and assistant professor at the Okinawa Institute for Science and Technology. And today he's going to tell us about the problem of time, relational observables, and quantum covariance. Philipp, the stage is yours.
Okay, yeah, thank you very much for the nice introduction. And I would like to thank all of the organizers for organizing this really wonderful looking seminar series, which I think will be very important also to communicate across approaches. And I very much look forward also to the other talks in the series and also to the discussion that will arise from that. And of course, thanks for letting me the guinea pig of the seminar series and speak today. So yeah, the organizers have asked me to give an overview of relational observables, but also to provide some, or to set the stage more generally for observables in gravity. And so this is what I will try to do in the beginning of the talk. So to talk more generally about observables and what we mean in gravity by that. And then later on, I will focus on the notion of relational observables, both classically and in the quantum theory. So I'm not entirely sure I will manage to finish all the slides that I have. That depends a bit on how we go. As far as questions are concerned, yeah, if you have any questions concerning comprehension, then please feel free to interrupt or write that in the chat. If there's any questions that will take a bit of a longer discussion, and maybe let's wait until the end of the talk. Okay. So yeah, so then let's maybe start straight away with the very basic idea of what are actually observables in general relativity. And so the starting point for this is the observation that, in fact, the action of general relativity with matter, in fact, is invariant under two kinds of symmetries, and that's both active and passive diffeomorphisms. So what I mean by that more precisely is that, well, at least when acting on the gravitational part, Passive diffeomorphisms are just, of course, coordinate transformations of some metric, as here on the right orbit on the right-hand side. But note that these are actually not generating a full group. It's rather pseudo group because coordinates are not always globally defined. The action is, of course, invariant under that. That's the notion of general covariance. But the action is, in fact, also invariant under active diffeomorphisms. And what I mean by that more precisely is like here, that you have the diffeomorphism group of the manifold acting on the space of geometries, or also matter fields on that. And so now we have that symmetry, or these two kinds of symmetries that are, of course, related. And having symmetries, what we would like to have, or the basic idea here, is that we want our observables to be invariant under these symmetries. And here, one thing to note is, so we can ask for whether we would like to have an invariance under only passive diffeomorphisms or active or both. And it's important to note that they're not exactly the same, these invariances. And let me explain that at the level of a scalar function. So a scalar function is just, well, it's a function of a manifold. It's defined independent of coordinates. And so the values it assigns to points is, of course, independent of what sort of labeling you choose. So in that sense, it is actually invariant under passive diffeomorphisms. But this object is not invariant under active diffeomorphisms unless it's a constant, because active diffeomorphisms will, of course, well, they act through pullback. And they will just reshuffle the relation between the relation between the values of the scalar field and the points of the space-time. So, but conversely, it turns out that if you require invariance, in fact, under active diffeomorphisms, that will also imply invariance under passive diffeomorphisms. So in that sense, this is a stronger notion. This will become hopefully clear throughout the talk, but maybe it should already be clear from this sketch here. So if you're invariant under active diffeomorphisms, that means that your observables only depend on the orbit, but not where you are on the orbit in the space of geometries. And then you can already guess that that should also be invariant under coordinate transformations or independent of coordinates. So in the sequel, when I talk about diffeomorphism-invariant observables, I will be mostly talking about invariance under active diffeomorphisms. So in that sense, we actually then have also a proper group, invariance group of the action. The diffeomorphism group is a proper group. And as we will see, this will not actually impede the predictivity of general relativity, because it will leave the relations between the physical degrees of freedom invariant. So you may, of course, ask, so why do we usually get away with coordinate calculations in general relativity? That's a very good question, and I will in fact come back to that later in the talk. In short, the answer is because although they're not gauge invariant a priori under active diffeos, they can always be made invariant under those. So, so one thing that should be clear, if you now require invariance under active diffeomorphisms, is that these observables will be highly non-local objects. And so, in fact, because of that, it's not useful to think of these diffeomorphism-invariant observables as functions on space-time. It's more appropriate or better to think of them as being functions on the set of diffeomorphism equivalence classes of solutions. So they are really, in an abstract way, you can think of them as being functions on this object here, where F is the set of dynamical fields satisfying the equations of motion. So you can think of it in the sense of a covariant phase space if you want, and you mod out by the diffeomorphism group. So you may, of course, ask then, well, that's a very abstract definition of observables. So what has that got to do with physics? That's a very good question. And as we will see, it will have actually quite a lot to do with physics. One thing that we can already say is it basically tells us that when we talk about localization, we shouldn't think about localization in space-time, so relative to space-time points, but what we should be thinking about is localization relative to one another. So that physical objects are in fact only localized relative to one another. That is, you localize relative to dynamical degrees of freedom. Okay.
Philipp?
Yeah.
There's already a question in the chat. Are you distinguishing between large and small diffeomorphisms? It has those which act non-trivially on the boundary of the space-time.
Yeah, so here actually, yeah, that's a good question. So here I'm actually, for the moment, just assuming a trivial action on the boundary. Okay, so one thing you will always hear, or you hear it quite often, is that it's very hard to construct interesting observables in general relativity. So interesting observables in the sense of being diffeomorphism-invariant. So one thing to note at first is that it's in fact not hard at all to construct at least formal diffeomorphism-invariant observables. So for instance, what you can do is you give me some scalar function, and then we can just integrate that as a density over space-time that is, of course, formally diffeomorphism-invariant. You can also do that in a multi-local way. But one thing is, it's important to note that these objects are in fact a priori not very interesting or useful, and that is because, well, they're very formal, so they may in fact diverge. So you can think of the scalar function, for instance, to be the square of the Ricci curvature, and suppose you have a curved manifold and you average that now over a non-compact manifold, well, that will generally give you divergence. But even if you have a convergence of your integral, then it's clear that such an observable is a highly non-local object that really doesn't tell you anything about local information in space-time, so they're phenomenologically really not interesting. So for making phenomenological predictions that we can test. So we are local observers, so we would like to have local information. And then the other thing to note is that as I have defined them here, these objects, in fact, this is completely independent of the dynamics. So in that sense, they're really kinematical diffeomorphism-invariant observables. So I have not required that this is defined on any solutions to any equations of motion here. And in fact, these observables, they can be applied to any diffeomorphism-invariant gravity theory. The definition would be the same. So it could be f of r gravity, GR, or any other gravity theory that you might like. So, but of course, we are more interested in more specific observables. And what we want to have is observables that encode local information so that we can do something like phenomenology. And the other thing is that the observables that we want to have, we want them to tell us something about the specific dynamics of space-time or the theory that we're interested in. So it should be somehow dependent on the dynamics. And this is why it actually gets very hard in general to construct such interesting observables that have these properties, because we are talking about localization in diffeomorphism-invariant context. So as we will see, that really we can only really do that in a relational way. So we localize dynamic degrees of freedom relative to one another. And the other thing is, if those objects, they will in general only be defined on solutions that will in fact enlarge significantly per theory the amount of possibilities that you can have for observables. But since they will depend on the dynamics, they will require to solve the dynamics. And in that sense, of course, we know that in general relativity, we don't have any general solution to the equations of motion. So in that sense, we shouldn't be surprised that in general, these are very hard objects to compute or construct. Okay, so much of the talk will be focused on canonical gravity. So let's maybe start with a brief review of the constraints in canonical general relativity. So we have some 3+1 splitting into space and time. And well, if you take your action and you do a Legendre transformation, then it turns out that this diffeomorphism symmetry of the action leads to the Hamiltonian, at least in the BAT, to be a linear combination of constraints. The form of the constraint is not so important for this talk, but one part is a so-called Hamiltonian constraint, and the other one, the so-called diffeomorphism constraints, and well, you get some boundary terms. So for most of the talk, I will be ignoring or assume there's no boundary, and I will come back to that at the very end. Hopefully I get to that. So while the form of these constraints is now not so important for this talk, it is important to know what they actually do. So they actually generate the so-called hypersurface deformation algebra. It's not exactly an algebra, but that doesn't matter for this talk. So first of all, these spatial diffeomorphism constraints, they really close on algebra, and it turns out they just generate the diffeomorphisms within the spatial hypersurfaces. And by contrast, the Hamiltonian constraint, it turns out that only on solutions it actually generates transversal displacements of that hypersurface. And so you can consider these objects on shell. So when you solve the constraints or the equations of motion to actually be a representation of your algebra of diffeomorphisms. And so it's a subtle point. There's a nice discussion of that in these references down here if you want to know more about it. Okay, so now that we have these objects, and in the canonical theory, these constraints, they generate the hypersurface deformations, and they're related on shell to the diffeomorphisms, we can ask about observables now in the canonical theory. And so what we want is now that diffeomorphism-invariant observables, so they should now Poisson commute on shell with these diffeomorphism generators. So that is, they should satisfy these equations. So these wiggly equalities, they're so-called weak equalities. That means they only have to hold on shell. So they don't necessarily have to be kinematical equalities. And in general, they will not be. So, but in that sense, what we see is since the Hamiltonian constraint also generates the dynamics, that objects that satisfy these conditions, they're constants of motion. And they're actually called Dirac observables. And so what we see now is, of course, already an indication of what is in the end the problem of time in the quantum theory. And the question is, how do we actually get dynamics out when we are dealing with constants of motion? And these are the observables of the theory. Okay, so just as a precursor for the quantization or the discussion of the quantization later on, so this leads to the problem of time. When you quantize these constraints, so what you want to do is you somehow impose these Hamiltonian and diffeomorphism constraints in the quantum theory. So what you want to have is that physical states, that they are annihilated by these constraints. That's basically the Wheeler-DeWitt equation. And so what I want to emphasize is, for the purpose of this talk, so I'm not going to be specific about how we impose these constraints. So in particular, we can be agnostic about whether the result of, or the resulting quantum theory, whether you want to interpret that as a fundamental or effective quantum gravity theory. So fundamental, that would of course be the perspective of loop quantum gravity or geometry dynamics, but you could also think of it in an effective sense if you want, for what I will talk about. So in the spirit of quantum gravity cross approaches, I will try to focus on information that will hopefully be of interest to more people in various communities. Okay, so now what is the problem of time? At the very basic level, there's many phases to it, but at the very basic level, it boils down to the observation that physical states that satisfy the constraints, they appear to be frozen in time, in quotation marks, because the Hamiltonian is also the generator of dynamics. And then we see, oh, it doesn't evolve in any parameter time. So that's why these states are often called actually timeless, but that turns out to be quite a misnomer. And similarly, from the diffeomorphism constraints, we could say, well, they are somehow constant in space, but usually people don't really call that spaceless, but well, they are invariant under generators that generate transformations in space. So, but in order to resolve that confusion, what is really important to note here is that when quantizing these objects, what we really are doing is it's a quantization of space-time. It's not a quantization in space-time. So these quantum states are not states in space-time, they're states of space-time and any matter contained in it. So in that sense, what one can really think of is that these objects are background time and spaceless. So they are not, like I said, they are not states in the space-time, but they are not by no means internally time or spaceless. And the basic idea of relational observables and relational dynamics is that we should be defining localization in space and time and the dynamics in a relational way, extracting it from the relations within the degrees of freedom inside that state. And so you can call it the problem of time, but really what most of this will be about, and the core question is, how do we actually localize in a background independent quantum theory when we don't have external references such as
Philipp,
yeah.
There's a question from Lee. Why do you say that the quantum state doesn't evolve in time when there's no clock represented?
Sorry, but well, so the thing is that so I'm not entirely sure if I understand the question very well, but the thing is that usually one would think, of course, as a Hamiltonian acting on some state in the sense of a Schrödinger equation as being something like I ddt of that state, and now we see, oh, that's zero. So if we think of the Hamiltonian as acting or as generating some dynamical flow, for instance, suppose it's a self-adjoint operator and we exponentiate it and it defines some unitary flow and some kinematical Hilbert space, then this condition here will imply that that unitary acting on physical states will just leave it invariant, so it doesn't evolve under that. So that's what I mean by it doesn't evolve under such a parameter time. Okay, so yeah, so let's so the menu for the talk here is basically, well, as follows. So at first, I will try to introduce the notion of relational observables at the classical level, also in generativity. And then I want to discuss these objects in the quantum theory. I will also talk about challenges and achievements. And then in the end, let's see whether we can also relate that to other approaches. Okay, so
sorry,
let's start.
Just another question. This is an unperturbed approach. So
yeah, right. So this here, I should have emphasized that. So here we're really talking about non-perturbative physics. So yeah, as far as relational observables are concerned, so let me tell you what the very basic ideas are. So I told you before that we shouldn't think of diffeomorphism-invariant observables as functions on space-time. Now, relational observables are such diffeomorphism-invariant objects, and in some sense, you can think of them as being functions on dynamical reference fields. And so the basic observation is, so this is an idea that really goes back to Carlo Rovelli. He was developing that a lot in the 90s. So essentially, the main observation is that all measurements in the real world, also in gravity, are relational. So whenever we do any observations and test general relativity, any of the measurements are done relative to some dynamical clock in the laboratory or whatever, an atomic clock on some airplane and so on. And of course, we localize relative to dynamical degrees of freedom. And so what we should be really doing is, well, the premise here is really that in the proper physical theory, there should be no external reference to which we relate anything. All reference systems or reference frames, they should be internal and physical, and thereby also dynamical. And so the basic question that arises is, how do we describe physics relative to dynamical reference systems? So one question that then immediately comes up is, what is actually a reference system? So the very basic idea is that a reference system, so we have now gauge symmetries here, and what we really want to do is we want to use dynamical reference systems to parametrize the flows of these constraints. So basically we want to parametrize the gauge orbits with dynamical degrees of freedom. And so what these reference systems should be, therefore, is they should be as non-invariant or asymmetric under gauge symmetries as possible. So if we have invariants such as Dirac observables, they are the worst possible kinds of reference systems. And then the other thing is we should, of course, have as many degrees of freedom, or the reference system should have as many degrees of freedom as there are independent gauge directions or as there are constraints. So from this, what we can see is then that reference systems or reference degrees of freedom will really be gauge degrees of freedom, but we will use them to build a platform for gauge invariant observables. So let me illustrate the construction of this in the case of reparametrization-invariant systems, such as, for instance, homogeneous cosmology or relativistic particle mechanics. So we have just one single Hamiltonian constraint, and there's no, well, it's a finite dimensional phase space. We don't have to worry about spatial diffeomorphisms. And now what we want to ask is, so we want to pick some clock function or time function t that we use to parametrize the flow of the Hamiltonian constraint and the constraint surface. So there's a sketch of the constraint surface and then the flows, gauge orbits generated by the constraint. And so what we want to ask for is now, what is the value of some observable of interest when this clock function t reads a value tau? And so this is something that, because these gauge orbits are also dynamical orbits in this case, this depends on the equations of motion, also on the solutions, and you can define such an object in this way here. So the alpha SCH is just the dynamical flow generated by the constraint, S is the parameter along the flow, and so then you ask basically what's the value of F at the point of the orbit when the clock T reads tau. And so this is an object that, as Bianca Dittrich has then later shown, you can write it in terms of such a power series here. And it turns out that this object is actually something that is reparametrization invariant, so it commutes weakly on the constraint surface with the Hamiltonian constraint. So in that sense, it is really a gauge invariant quantity. But at the same time, because we now have these parameters tau, so the tau is not the dynamical parameter, it's just the different readings of your clock variable. And so what we get is really a one parameter family of constants of motion. So these are, in that sense, they are evolving constants of motion, and the whole family really encodes the whole dynamics along such a flow. And the way you can think of these gauge invariants, this gauge invariant evolution relative to that clock t is basically as taking some t equals constant surface in your phase space and scanning with that through the constraint surface, and then asking what values f takes on that as you scan through that surface. And you can think of these objects as being really gauge invariant extensions of gauge fixed quantities. So gauge fixed quantity, because you ask what's the value of f when t is tau, so that's really like a gauge fixing condition. But then this object here actually turns out to extend that that assignment to the entire orbit, so it becomes a constant of motion. So if you have never seen that before, maybe let me give you an example.
There are two quick questions.
The parametrized particle, so it's just a two-dimensional phase space.
Philipp, there are two questions.
Sorry?
There are two questions. So one is, the brackets are Dirac brackets in the previous slide.
No, these are on the constraint surface. You can, these are Poisson brackets, yeah.
And the other question is, who can read the clock?
Yeah, that's of course yeah, so a question that is in this case not considered. So I mean, this here is just just in principle an abstract definition of how you define dynamics relative to certain dynamic degrees of freedom. But of course, you could always think of if you have some laboratory that the clock that you're actually using, that this is something like a clock that that sits in your lab, and then you have some observer that would be somehow externally that would not be modeled as part of the system here. But maybe let's not get too much into that discussion here. We can talk about that later. Yeah, the parametrized particle. So you have a two-dimensional phase space. Well, just yeah, in one dimension, the free particle. You can parametrize that to a four-dimensional system. In this way, you just take your t and make it a dynamical object, and have some gauge parameter s, and it's kind of clear that this dynamics here will give an equivalent dynamics to this one here. If you evaluate it on solutions, it will just give you the same result, basically. Another way to see that is if you do a Legendre transformation of these objects, you get a constraint that takes this form here, and now you can construct such relational observables, this power series. And you can ask, for instance, as an example, what's the relational evolution of this little q, the position of the particle, as t reads some value tau. And then if you do that, that power series, the solution looks like this. And then one thing to notice, these are gauge invariant objects. You can now gauge fix that, that object here, for instance, to t equals 0. If you want, the value of that thing will still be the same. And then what you see is that the gauge invariant dynamics that you get that's encoded in this tau is really exactly the same as what you would have gotten from the unextended original free particle action. So it's of course a ridiculously simple example, but the principle works also in more complicated systems. So there exist, in fact, other than these power series constructions, also integral representations of relational observables in the literature, especially Don Meroff has also worked on this. So they usually take this form. It's kind of trivial to see that they're actually fully equivalent to that power series. But maybe let me not really go through the argument in detail in the interest of time. But well, the main message to take away is these integral representations are really equivalent to the sum representations. And they will become handy at some point later as well. Now, the more interesting question is, of course, okay, you can treat these objects well, in simple systems such as homogeneous cosmology or whatever, this parametrized particle, but can we really do such constructions of relational observables also in full general relativity? And so, or in field theory. And so the answer to that question is yes, one can do it. So formally, it is possible to do. So why that is formal, I will explain on the next slide. But let me just give you a hint of how this happens. It becomes, of course, a lot more complicated now in field theory. So in this power series, you saw the constraint appearing, and well, you have these nested Poisson brackets of the constraints with the observable of interest. So when you are now in field theory, such as in canonical GR, well, the constraints are then going to be smeared over the hypersurface. So you have generally integrals appearing in your power series that becomes, well, kind of a convoluted object, but you can construct it. But you can simplify such a construction tremendously when you use ultra-local quantities, such as, for instance, scalar fields. So what I mean by that is, suppose you are interested in some scalar field O, and you want to know, so this is now in GR, and you want to know what's the value of O when you have certain 4 reference scalar fields that at least locally parameterize a good parametrization of the orbits, or if you want that provide at least locally a good coordinate system. And then you want to ask what's the value of, so in that sense, these reference scalar fields are dynamical rods and clocks if you want. And now you want to ask what is the value of this O of interest when these scalar fields read particular values tau. This construction simplifies tremendously, and that is because these scalar fields, when you act with them, when you look at the Poisson brackets for the constraints, they just give you a lot of delta functions because, well, scalar fields really only depend on the point in the hypersurface where you are, but not on any other points. So they're already sort of automatically invariant under constraints elsewhere in the hypersurface. And so in that sense, all these delta functions that arise, they will actually be killing the integrals that otherwise appear in this power series expression. And then you get a power series that well, it's somewhat simpler, and that in fact, in the end, really only depends on 4 parameters tau I. So the values that these reference fields are supposed to take. And so I'm not going to explain that in more detail. That goes beyond an overview talk. The main message is these objects exist. And in this case, you can think of this observable here again in such an integral representation in the following sense. So you have your observable of interest, the scalar field, and then well, you basically throw in a delta function that clicks when these scalar fields read these parameters tau I. And then you have a measure correcting factor. Okay, so yeah, so these objects, they can be generalized also beyond scalar fields. But in general, such a construction is formal. And why is that formal? Well, because we don't know a priori if this power series or the integral converges. That depends very much on the dynamics. And implicitly, in writing down these observables, you are actually solving the equations of motion, at least implicitly. And so, and of course, for full general relativity, in general situations, we don't have a solution. And so in that sense, such a construction is formal. And so the main message is that these concrete relational observables that you might be interested in, they will depend on the dynamics. And so they will depend on the chosen reference fields, on the matter content of your space-time, on any additional symmetries like isometries or whatever, or the topology boundary conditions and so on. So in general, these are very complicated objects and that will depend very much on the specific space-times that you're considering. Another challenge that arises is that generically, we won't have distinguished choices of reference fields. And so in that sense, we get a multiple choice problem of reference fields. And then the question is, which ones should we pick? And then another issue that arises is in fact a so-called global time problem or the global problem. And that's that generally you won't have globally monotonic reference fields in general, in the sense that they will provide globally in space-time a good dynamical coordinate system. And so in general, that means that these relational observables, they will be multi-valued in general space-time situations, but at least locally, that's fine. So to illustrate what I mean by that, you can consider, for instance, the closed Friedmann universe with a massive scalar field. This generates a very complicated dynamics in phase space. So and if you have here, this alpha is the log of the scale factor, phi is the scalar field. If you want to know now, for instance, what's the value of the scale factor when phi is 0, well, then there's a lot of different solutions or answers to that question. So that illustrates that multi-valuedness issue. But at least locally and classically in phase space, you can construct such observables. So, but in the quantum theory, that is an issue. Okay. Yeah, so to provide one example where also in the field theory case, you can make these formal power series constructions actually explicit or concrete. There's a special matter system where you can do that, for instance, and that is general relativity with pressureless dust that was introduced by Brown and Kukash in the mid-90s. There were also similar models discussed elsewhere. And the basic idea is we have now total action, that's the Einstein-Hilbert action plus a dust term. So I'm not going to go into the details here, but the basic point is that we have now a dust 4 velocity. This is this u here. And this we can decompose into the proper time of the dust particles and into co-moving coordinates, but there are now dynamical fields in space-time. But it turns out that the dynamics is such, well, that these dust coordinates, the co-moving coordinates, well, they are always preserved along the different fluid flow lines. And while the proper time grows monotonically, of course, along these lines. So in this sense, these dust coordinates provide what you can call a perfect dynamic reference field. They really parameterize the space-time entirely in the sense here. So we can use the equal proper time hypersurfaces to define hypersurfaces, spatial hypersurfaces in space-time, and we can label points through the co-moving coordinates. And in this case, it turns out that you can actually turn these relational observable power series constructions completely explicit. So I'm not giving you the entire explicit form of them because, of course, they look somewhat convoluted, but you can actually work them out and well, they converge sort of. And so you can construct the relational observables, for instance, for the the spatial metric components or its canonically conjugate momenta as the dust coordinates take some particular values. And then, although these are rather complicated objects, it turns out that they're still canonically conjugate objects. So if you look at the Poisson brackets of these relational observables, they still satisfy canonical commutation relations, at least in the Poisson bracket sense. And so, and another thing to note is that here in particular, they commute at space-like separation. So we see that although these relational observables are kind of convoluted objects, they even encode causal relations in that sense. And there's in fact a more general argument that is due to Bianca Dittrich using her power series, where she again has, so it's actually not in any paper, she has only done that in talks. But the basic statement is that when you have, again, the situation of scalar field O and you want to know what its value is when certain scalar clocks and rods take other particular values, and the different sets of values that you're considering are space-like separate, then the Poisson brackets of those objects, they will in fact also be zero. So the main message to take away from this is that, yeah, so although the relational observables are really complicated objects, so they're gauge invariant extensions of gauge fixed quantities, they still preserve a lot of information that is still also encoded in the objects, the gauge dependent objects of which they provide gauge independent extensions. And in particular, one can encode causal relations and locality in a relational manner. Okay, since it's very complicated to construct such relational observables in practice, and we might not need to know them for a full GR, it is interesting to know at least that one can also turn these power series expansions into perturbative expansions, where you basically construct approximate Dirac observables or relational observables around, for instance, phase space points such as Minkowski, so perturbative gravity you can do in this sense, or also phase space sectors such as homogeneous cosmology. So I'm not going to go into discussing this, it would derail this talk a bit, but yeah, so there have also been further developments in this direction, in particular to discuss also cosmological inhomogeneities. Okay, one thing to note now is, so we have now dynamic reference fields, and I mentioned before there's this multiple choice problem, so generally there's no distinguished choice. So what we would like to have is now a way of actually, well, to have some sort of covariance where we can translate between the descriptions relative to different choices of reference system. So I'm not going to explain that in detail here. I just want to explain the general idea of it. So the general idea is that, well, we are working on the constraint surface, so we have to work on solutions. And on the constraint surface in phase space, you always have a redundancy in the description. And that's, of course, because we have the, well, it's symmetry induced, or it's induced by the constraints. So we're only in the submanifold of phase space. So clearly not all the kinematical degrees of freedom are independent there. But in fact, also physical gauge invariant degrees of freedom are not necessarily independent. And there exist many different ways in which we can split the phase space description into gauge and gauge invariant degrees of freedom. And it turns out you can relate those by canonical transformations. And the main idea is that whatever we consider as the redundant degrees of freedom, that we relate that or make it equivalent to the choice of reference system. So remember, the choice of reference system, it's related, their gauge degrees of freedom, and we will consider those as the redundant ones. And then, well, the description or the redundancy-free description afterwards, that is what we will then consider as being a description of the physics relative to that choice of reference system. The main idea here is that we don't want to describe the reference system relative to itself in order to avoid self-reference problems. And so in this way, we can, in fact, describe the same gauge invariant information in many different ways. And yeah, in these many different ways, we can consider those as being different reference system perspectives. And well, in at least finite dimensional systems, we have constructed explicit examples of how you can relate the different relational descriptions to one another. And I should note that when you extend that to field theory, this is actually related to field redefinitions, for instance, in covariant phase space. That's an observation that I should thank Daniel Oditi for. Okay, so now one of the important questions that I mentioned at the very beginning as well. So now we see we can construct something like relational observables in generativity, but why do we usually get away with coordinate calculations generativity? So phenomenological predictions of GR don't usually use Dirac observables. And why are they still successful if they're not gauge invariant? So the main message is that because they can always be made gauge invariant, so more precisely, what one should keep in mind is that these relational observables here, they are gauge invariant extensions of gauge fixed quantities. So what is this function f here? Let's recall what it is. It's this capital F. What it is it's the value of this whatever function of interest f when the reference systems reads particular values. So in particular, it means the set of values of these relational observables, they're the same as the set of values of these little f's. And so, of course, the values is what we're ultimately interested in for phenomenological predictions. And the point is that you can always make these values of the little f gauge invariant, at least in principle. And this, for instance, happens quite literally in that case of this Brown-Kukash dust model that I discussed before. So for instance, we might want to be interested in the value of the Ricci curvature scalar. We can compute that as a function on space-time in some coordinates. But because we now have this perfect dynamical coordinate system, we can relate any such whatever coordinate choice we have made, x mu, to the readings of the dynamical coordinate system, the dust coordinate system. And in that sense, we can actually just translate the value r of x into a relational observable that really contains the same values and the same information, but in a gauge invariant way. And but the difference is now that this object is actually function on the equivalence classes of solutions and not anymore on space-time in that sense. And so this is an argument that holds more generally. So I mean, here in this case, of course, it works perfectly because the dust coordinates are perfect, but you can generalize that argument. Now, then you might wonder, so why should we then bother at all about Dirac observables if we can get away with coordinate calculations? One thing to note is here that, well, from a conceptual point of view, it is more satisfying to have these relational observables. They give a conceptually more appealing picture because all the localizations are now relational, and that really corresponds to what we have in any observations that we do in the universe. But more importantly, also now for quantum gravity, the reason these objects are actually interesting is we cannot rather ask, why can we not get away with coordinate calculations in canonical quantum gravity in a non-perturbative setting? And that is, here we have to recall these objects here when we want to quantize these constraints and throw them on physical states. Remember that these physical states are background time and spaceless, so they are not states in some space-time. And so rather you should think of these physical states that satisfy the constraints as being in fact entire or corresponding to entire orbits of the diffeomorphism equivalence class. So it's rather so the thing is, so there's something that becomes clearer when one discusses constraint quantization. Every physical state really corresponds to an entire equivalence class of so-called kinematical states in a larger Hilbert space. And so what we see is now when we actually work in canonical quantum gravity, the physical states we want to be working with, well, they correspond to equivalence classes of the diffeomorphism group. And in fact, we can, of course, thereby also superpose different equivalence classes. And so therefore, for the full quantum theory that we want to construct in this way, we need actually observables that are defined on equivalence classes. And so on this is why these Dirac observables are very important for canonical quantum gravity. And now we see also, of course, the question then is, how do we define localization also in such a quantum theory that is defined in terms of such equivalence classes of diffeomorphism group elements? Well, at least in principle, we know now how to do it, namely in a relational way. And so in the last part of the talk, I want to tell you a bit about how one can translate that into the quantum theory. There's, of course, this will be much more complicated, but in principle, at least in many situations, you can do something about this. One thing to note is that there exist various approaches to relational dynamics or to the relational paradigm in quantum theory. One is the so-called Dirac quantization. Let me not review that here. I see that time is progressing. It's basically the idea that you first quantize and then you solve your constraints in the quantum theory, and then you want to on the space of solutions to the constraints, you want to somehow construct such Dirac observables. And there exists this reduced phase-based quantization. This is where you solve your constraints classically. You remove all gauge-dependent degrees of freedom, and you only directly quantize gauge-invariant observables. So you have no more constraints in the quantum theory. And then there's the so-called Page-Wootters formalism, where you essentially condition your physical states on reference system orientations. So these different approaches are not in general equivalent. In particular, Dirac and reduced quantization are not in general equivalent. And so the question then arises, which one should one pick? Let me now, in the sequel, tell you a bit about these different ways of doing that. First of all, before I talk more specifically about how one can construct relational observables in the quantum theory, which is much more complicated, let me tell you something about what has been done, at least at a general level. And so classically, it is, of course, hard to construct them. The quantum theory much harder, but there exist some solvable models. So in quantum cosmology, there exist zillions of models, and well, they're mostly homogeneous, but some of them also including inhomogeneities. And then in that setting, both the Dirac and reduced method have been successfully carried out. And I mean, it's not worthwhile to really mention names here because there are so many of them, different papers in loop and related with quantum cosmology. But one can also do a diffeomorphism-invariant scalar field theory, Dirac quantization. This can also be carried out to completion. Then, and then there's in fact also two, at least in loop quantum gravity, well, sort of semi or hybrid Dirac or reduced quantizations of of this dust model that I told you about before. So there you basically take advantage of the fact that you can construct a reduced phase space. You know what the gauge invariant degrees of freedom are, and you can quantize those. So this can be done. And then there exists also a way of doing that with a massless scalar field. So in that sense, you can say there exist even full quantum gravity models. So however, well, they use pretty special matter, and it's still very hard to make computations. But anyway, at least in principle, it shows you that you can do it. So let me now tell you a bit about how one might try to somewhat more systematically quantize such observables. So let's make some restrictions. Suppose we have now just a single constraint and we can split it into a clock and a system part where consider some system that evolves relative to some clock. And let's suppose for the moment that the clock Hamiltonian, that it has a continuous spectrum such that it actually generates a monotonic clock in a group that's diffeomorphic to the reals. And the system Hamiltonian can be arbitrary. So what we want to do is quantize now this power series of relational observables. And here we will do a little trick to simplify it first classically. And what we can do always locally is choose some time function t that is canonically conjugate to your clock Hamiltonian. So and thereby also to the constraint. In fact, if you do that, you can really simplify that power series in such a form here. It looks a lot simpler. And then, well, we would like to quantize some object like this now. And basically what we need now for the quantum series is some t or a clock variable that is similar to the one that we used here. So here it is important to note that this cannot be in general a self-adjoint operator t, because for bounded Hamiltonians, as is well known, you can't have such perfect self-adjoint operators that satisfy these conditions. But there exists a way out, and that is by using so-called covariant clock POVMs. That's something I was introduced to by my collaborator, Alex Smith. So what are these objects in a nutshell? Well, you can define, basically covariant clock states in terms of the energy eigenstates of your clock Hamiltonian. The sigma is just a degeneracy label. And well, if you construct it like this formally, what you can see is if you throw the unitary generated by your clock Hamiltonian on it, then these states will evidently have that property here, such a monotonicity properties. You can think of them as being coherent states of the group generated by the clock Hamiltonian. Now, using these objects, you can construct something that you can call, well, that is actually POVM, and you can construct so-called nth moment operators. That's like a generalization of the spectral decomposition of self-adjoint operators in this form here, where this ET is just basically written in this form, so you use the clock states to do that. And these objects here, they really give you a generalization of canonical conjugacy in that sense here. The price you pay for that is that these objects, these nth moment operators are not in general self-adjoint operators, but they satisfy the properties that we want to have. And so basically for these observables, these power series, you can now use these covariant clock POVMs. And basically, if I go back here, you take this expression here, and then you throw that the nth power of the observables you replaced by these nth moment operators. Then you get this object here. You can put that into a different form, where this here really is a so-called G-twirl. So it's basically an incoherent group averaging over the group generated by the constraint. And what does it do? So it really averages the projector onto a certain clock reading, and your observable fs of interest, well, it averages that over the group. And what you can show is that these objects indeed commute with a constraint. So they are, in that sense, gauge invariant. That satisfies various other nice properties. And these objects, they are in fact very useful. So we could use them also to show equivalence with another approach to relational dynamics that has been floating around, and that various people now also in quantum foundations are very interested in. And I've even seen that in holography, people mention that. So and that's the so-called Page-Wootters formalism. So what's the basic idea here? So you have physical states satisfying your constraint. And well, you use such covariant clock states, and then instead of working with observables directly, you define something like conditional probability. So you basically define the conditional probability that some observable fs of interest has a given outcome fs, well, given that the clock reads some value. And then you can define that by extension of the Born rule in this conditional manner here. And well, what you can show is, in fact, that when you condition the physical states on these clock readings, well, it's only a state in the system Hilbert space, really, that this object satisfies the Schrödinger equation. So people get very interested in that. A priori, it seems to be quite different from this relational observable picture, but it turns out that so something that we have recently shown, that this is in fact completely equivalent to the relational observable picture. In fact, you can explain these conditional probabilities as being expectation values of relational observables and so on. I'm not going to explain that in detail here, but the main message is you have an equivalence. And if you're interested in the Page-Wootters formulation, then you should also be in particular interested in relation to quantum observables. And in fact, we also showed another equivalence with well, another way of doing relational dynamics, but I see that time is progressing very fast. So let me skip that. Well, okay, one thing to take away from this is in these equivalences, so you have now basically different phases of the same relational quantum dynamics. And
just as a warning, you have 10 minutes left.
10 minutes, okay, yeah, that's a challenge. Yeah, so the main message to take away from here is that, I mean, this Dirac quantization and these relational observables, that is really a manifestly gauge invariant formulation of your relational dynamics. And these other sort of reduced, symmetry reduced quantum series, including the Page-Wootters formulation, you can really think of them as being gauge fixed formulations of the gauge invariant theory, but they're equivalent. Okay, let me skip this here in the interest of time. One thing maybe I should note is that this trinity, so it's so this equivalence of these different approaches to relational dynamics and the quantization of relational observables this can in fact be generalized to arbitrary locally compact Lie groups, so much more complicated systems under certain conditions. Yeah, I will not talk much more about that, but just as a heads up that these structures are much more general. Okay, let me mention now something about quantum covariance. So I mentioned before classically that you have something like, you can define a dynamical notion of covariance. So we have dynamical reference systems now, and we can translate now the descriptions relative to, classically relative to different choices of reference system into one another. And so the question is, can we do something like that in the quantum theory as well? And the answer is yes, that is possible. The main observation to do here is to recognize these physical states not as being something timeless, but rather as being a reference system neutral state. That is as a description of the physics prior to having chosen a reference system relative to which we describe the dynamics of the remaining degrees of freedom. And so you might ask, why is that possible? And so that's very similar to the classical case. The physical Hilbert space as the space of solutions to the constraints is like the quantum constraint surface. There's a lot of redundancy in the description of the physical Hilbert space. And so there's many different ways in which we can describe the same invariant physical states. And likewise, in terms of the observables and the different ways in which we can describe the same gauge invariant information, we can relate that to the descriptions relative to different reference systems. That's the basic idea. So one thing that I didn't really explain here is one can always define such well, sort of reduction maps that remove the redundancy in the description. One can also do that classically, and you can interpret those as quantum coordinate maps. Let me just give you sort of a pictorial interpretation of that. So the main idea is that, so we have our physical Hilbert space that is like this reference system neutral description of the physics, and then we can define something like quantum coordinate maps that are in fact quantum symmetry reduction maps that in fact also appeared in this trinity before. And then the images of that you can interpret really as a description of the same physics, but relative to different choices of reference system. And then if you want to relate the different descriptions to one another, then you can do that in a compositional manner, just like coordinate changes on a manifold, except that here, well, you're dealing really with maps between Hilbert spaces, and you map always via the physical Hilbert space. Well, there is, in fact, what you can show is, and that gets kind of interesting, that many of the physical properties, they actually depend on the choice of reference system. So I think I will not describe that here. So there's various references that you can read if you're interested in that. But yeah, the main message is that although we describe the same physical situation, the way this is being described can lead to some striking things, such as that entanglement becomes, for instance, dependent on the choice of reference system and so on. But okay, okay, let me maybe also skip this one here. So one important, so you can ask me about this later. You can ask about what about relational observables when you have chaos. So that's a very important topic. But let me maybe not mention that here because we also want to talk about other approaches and connect to other approaches. And let's come back to an important topic, and that is in fact space-time localization versus relational localization in quantum theory. So I told you before that at least classically in a non-perturbative way, you can encode in a relational manner even causal relations in locality. And so you might ask, so what about the quantum theory in that case? And so there's some interesting sets of papers by Giddings, Merrill, Hurdle, and also Giddings and Lippert, where they analyze some questions like this. It's in the context of effective canonical quantum gravity. So here they consider relational observables in such a, for example, like this here in an integral representation. So they should be regularized, but let's leave that aside for the moment. But what they show is that these relational observables really only permit an approximate space-time localization. So you have of course, a localization relative to your dynamical field, but that's not the same thing as the localization relative to some space-time manifold. So here there's some space-time manifold because that's effective gravity. And the basic statement here is that the fluctuations of your reference fields, they basically ruin the exact localization in space-time. And now there's then some more recent work on dressed observables in linearized quantum gravity. So here again, you have some, so it's a perturbative argument here, you have some background space-time. And this is something you will hear Will talk about. And the main, or one of the main results there is that if you take so-called dressed observables, so you ask, for instance, you ask for gauge invariant observables, so that commute with the linearized constraints of a scalar field, then it turns out it always carries some gravitational dressing. And these objects, they always, they turn out to generically violate microcausality in the sense. So even if these XX prime are space-like, they will generically not actually commute. And so that raises a question of locality in a gauge invariant context, at least perturbatively. And so one might ask, does this rule out, in fact, in the quantum theory, defining locality in terms of commuting subalgebras of Dirac observables? And so to me, the answer to that is not completely obvious. I would say not necessarily, because one thing to note here or to emphasize is that these arguments here are really effective or perturbative. So you already have some sort of notion of space-time to begin with. And so there's, of course, a subtle interplay between perturbative and non-perturbative observables. So this background space-time, or space-time, especially here, this background space-time, it must have emerged from somewhere, so some more fundamental description, whatever that is. And so, you know, from a non-perturbative point of view, it may be that that more fundamental description is some canonical quantum gravity theory, in which you still have Dirac observables, and it might actually still make sense, at least in a non-perturbative way, to define locality of subsystems via commuting Dirac observables. And so at least classically that works. So maybe in the quantum theory it does too. The answer to this is not completely obvious to me, again, because there's a subtle interplay of perturbative and non-perturbative physics here. And actually, I would be interested in hearing Will's opinion on this. Okay, so maybe as another point, maybe I still have 3 minutes, if that's allowed. Let me talk also about relational observables and boundaries. So in the discussion so far, I've ignored boundaries. And that's because most of the discussion on relational observables is in that context. But of course, there's a very large community that's very much interested in boundaries. And so we can ask what happens actually in that case. And so there's a very interesting paper by Don Merrill from 2009. So just in a nutshell, what does it do? So it considers, well, among other things, ADS-like spacetimes. And here, again, you know, as we have seen in the very beginning, on shell, the Hamiltonian, when you have boundaries, is really just a boundary term, because in the bulk you just have constraints. And so what Merrill argued is that this in the quantum theory leads to what he calls boundary unitarity. And that is, so if you have your ADS-like space-time like here, and you have some space like hypersurface in your boundary, you can associate your boundary observables to this, so some algebra. And it turns out that your Hamiltonian, in fact, there will be families, or there will be various Hamiltonians, because it depends also on whatever, some vector fields in your boundary along which it defines the flow. But anyway, so any of such boundary Hamiltonians, it will be a function just of the it will just be an element of the boundary algebra. Now, if you take any other element of the boundary algebra, then if you compute the time evolution of that, it will define you an automorphism of the algebra. So in a sense, you can say that the information that is present at the boundary at any time t1 will also be present at any other time t2. And so, but this does not necessarily mean that the boundary observable algebra encodes, of course, the full information about the bulk. And that is, well, still an open question. Does the boundary observable algebra, how much does it know about the bulk? And that has also led to a very interesting paper by Ted Jacobson and Philipp Höhn, where they discuss the so-called boundary information paradox that's really analyzing this. And it really hinges on well, if the boundary is unitary and if it knows everything about the bulk, maybe then there isn't an information paradox, but the argument is of course much more subtle. But anyway, it's a very interesting read. It's, however, more of a conceptual paper, I would say. And then there's also a recent paper by Steve Giddings where he uses also this argument by Don Meroff. I should say also this paper by Ted and Philipp is based on the paper by Meroff. So this later paper by Giddings also uses these observations by Don Meroff to basically argue using these linearized constructions of diffeomorphism-invariant observables. So he's basically arguing that a holographic map for the full theory should be actually related or should be requiring solutions to the non-perturbative bulk constraints. But if that is actually true, then well, we should be actually interested in bulk relational observables because those are the objects that describe what happens inside the bulk. And I think these relational bulk observables, they will become probably maybe a key for the resolution in this discussion here. And well, the key question, well, so far, you know, in this discussion, really what happens precisely in the bulk is, well, is sort of ignored, at least at an exact level. And well, it really boils down to the main question is how much do the boundary observables know about the bulk relational observables? And it's of course not an easy question to resolve. There's a very interesting paper by Dan Harlow and Wu on the covariant phase space with boundaries, which I think might be useful for at least starting to address that question. Okay, let me maybe briefly talk about relational observables also in other approaches. So there's of course also another talk by Kasia Reisner on basically perturbative algebraic quantum field theory approach to quantum gravity. Relational observables also appear there. So Kasia has in particular also worried about locality and relational observables. And so here, I hope she will also talk about perturbative versus non-perturbative locality and maybe what her opinion is on these locality issues that were raised by Will and Steve Giddings. Then there's also a talk coming up by Renate. And there's some very interesting developments on a new geometric non-perturbative observable for causal dynamical triangulation. So Renate is going to talk about observables in the discrete. And so this is quite a feat so far. I mean, it's a non-perturbative approach. It's of course very different from the continuous stuff that I've been discussing here. But at least, well, you know, have a sort of quasi-local observable for the geometry in the bulk, namely this Ricci curvature. And so one thing I'd be interested in is whether that might actually provide an ingredient for something like a relational observable in CDT. We just mentioned that there have been descriptions or discussions of effective relational observables with Ricci curvature also in this paper. So I'm not expecting that this can be immediately translated to CDT, but perhaps that might be worthwhile for some discussion. Okay, so one can of course also ask about asymptotic safety. Let me not discuss that here because I think my time is up. And other interesting questions is what about the S matrix, edge mode, soft charges, and so on, and relational observables. There's some interesting discussion by Meroff, at least on the S matrix. But generally, well, the answer to those questions is not entirely clear to me, but presumably relational observables may also play some role there. Yeah, so the summary of this talk. Yeah, I've talked very widely about relational observables. So main message to take away from my perspective is they are conceptually very appealing objects from a philosophical point of view. So, I mean, the basic idea is really you have no external reference. All reference systems are physical. We should always localize relative to dynamic degrees of freedom. That's ultimately also what we do in any measurement. And so this is really a formalization of what we do in observations. they are relevant in general relativity. So you can formulate that. Of course, it's a very complicated object, but in principle, you can at least do it. And because they are relevant in general relativity, I think these are actually objects that will be relevant in various approaches to quantum gravity. And we already see that they appear in one way or another in various quantum gravity approaches. And I think there's potential for more. So in principle, at least these relational observables, they might provide some common ground for quantum gravity cross approaches, in the sense that this is of course a very long shot, that they are sort of approach independent tools, at least in they should be for some low energy effective regime that might be very useful for ultimately comparing predictions of different approaches. So that's the main message. I'm not going to summarize all the other things that I discussed here. Let me just throw them in color here at you, and I think I should probably stop. And thanks for your attention.
Yeah, thank you, Philipp. Thank you very much for this great talk. And we still have time for questions. There have been quite a few questions in the chat during your talk. And maybe we start with Lee Smolin, who had a question, who was waiting for quite some time. You can.
May I give the question, if it's my question?
Sure.
Because I'd like to say it more generally, and I hope generously. Philipp, it's a wonderful summary of the issues, but something concerns me, and it's not in the exact details of your talk, but it's in the fact that not all, but many of the issues you raise and many of the approaches you raise were understood by the time of Chris Isham and Carol Kukash and Peter Hijek and Peter Bergman, which is to say before my time, as having problems when you come to applying them to the quantum theory, such as issues of operator ordering and divergences, such as issues of defining the physical inner product, the issue that the Page-Wootters defines probability in that context, which is not conserved and don't add up to one.
Actually, many of these issues have been resolved, I should say.
Well, it would have been good to have your talk focus on that, rather than give the classical theory in.
I mean, of course, I mean, so many of the issues that were raised in those have not been completely resolved, but some of them have been resolved. And for instance, one of which you mentioned here, I mean, I didn't discuss this in this talk because I wanted to give more of an overview, is, for instance, you talked about the criticisms of Kukash against the Page-Wootters formalism. So they have been actually completely resolved by us in our recent papers. And that's thanks to this equivalence, this what we call the trinity. So thanks to the equivalence that we have shown now for a fairly wide class of models where we showed the equivalence of the Page-Wootters formulation with the Dirac quantization and relational observables. And so actually I talked about this recently. Sorry.
Just to stop you there, that's very good news, and I wish you'd emphasize it. But at the same time, in a real dynamical approach to quantum gravity with real physical propagating degrees of freedom, do we have any hope of computing these Dirac brackets or these physical observables? The formal power series you write down are intriguing and interesting, but we've been thinking about them for 30 years. And if there's a way to resolve the field theoretic issues, such as divergences, regularization, without losing the gauge-dependent properties, I don't know of it. So,
well, so I mean,
register that caution.
So I mean, of course. So I mean, what I fully agree on is, of course, the the question what happens in the field theoretic case. Totally, and of course, it's much more complicated than classically, and already classically constructing these power series. I mean, it's a formal construction a priori, and it depends very much on your dynamics, as I try to emphasize. And of course, for full quantum gravity theory, this will be horribly complicated. There's no question about that. And in that sense, there's indeed progress on that front. Yeah, I don't really see very much in that direction. It's just untractable at this point, because at first we would also need to know what the physical Hilbert space is in quantum gravity. And of course, apart from these examples that I gave, we don't know that. And so that's why, I mean, many of these questions are currently totally out of reach. I fully agree on that. So I was not trying to emphasize here the point that you know, all of this is totally clear how to do in the quantum theory. Not at all. So I mean, I actually also wanted to emphasize challenges, and in fact also challenges such as Newman's worry. You know, what happens in the presence of chaos? Even classically, that's already a challenge. In the quantum theory, it becomes way more complicated. But there's still maybe ways of getting around this in terms of interpreting your dynamics rather than in terms of, I mean, it's something that I wanted to discuss here, is that even if you don't have concrete relational observables on your Hilbert space, you might still be able to, in fact, interpret your relational dynamics in terms of what you might want to call an S-matrix interpretation, where you take kinematical states corresponding to, you know, your clock variables reading certain values, and you have some observable that, some kinematic observable that takes some values, and then you take the group averaging projector, and then you interpret that as giving you, something like transition amplitude, some dynamical information. So there is at least maybe some hope of going around some of these issues, at least as long as you can know what this group averaging projection is, of course. But
good luck, genuinely, good luck with it.
Yeah, but again, sure, I agree that in the full theory, of course, I mean, there's I mean, it's a very complicated problem, of course. Huh? But at least for simpler systems, I mean, various of the issues have been that were raised by Kukash and so on have at least been addressed. Some in simpler contexts also resolved. And that's definitely a message I want to convey.
So maybe we move on to the next question. So I think Brian Pitts had a question in the chat during the talk. You would like to ask a question?
Yes, thank you very much. Thank you for the talk, Philip. My question came kind of late because it took me a while to get set up. We often hear about, say, the diffeomorphism or momentum constraint generating some sort of symmetry. But since it doesn't do anything to the lapse or the shift, I'm kind of wondering what this transformation is supposed to be. And Bianca kindly suggested an answer here, but I think she may have assumed something about matter reference fields. And my question was intended to be prior to that and fairly early on. A transformation that leaves the lapse and shift alone, but changes the spatial metric and the canonical momentum. And what does that mean physically? And how does it relate to coordinate transformations, if at all?
So I don't know what Bianca has said to this. Maybe Bianca wants to, I mean, if I don't know.
Well, maybe if I can comment, if you use clocks which are parametrized by tau, and the clocks can be either scalar fields, they can come from matter, or they can be gravitational degrees of freedom. These clocks define you a coordinate or a slicing of your spacetime and a coordinate system, which is phase-space dependent, and that allows you to actually express the full matrix, so all components of the matrix in this gauge fixing. And technically you get all these, this matrix expressed in a reference system, and it is then an invariant. And that has been, again, already worked out by Kukash. So they are fully, these observables are fully invariant under transformations, under diffeomorphisms. And Philip has shown these two formulations. One was the power series, that is a canonical, that is everything expressed in canonical terms, and what he calls the integral representation, where things are covariant, and you can use either of them to show that they are diffeomorphism-invariant.
Okay, thank you.
So as a next question in the chat, we had Hank some time ago. Would you like to ask your question?
It's mainly just a comment, really, because from what I've read about just ordinary QM, like no background invariance or relativity, really, what happens is that if you try to quantize like polynomials higher than 2 in P in the momentum, then what you encounter basically contradictions in the Dirac bracket, and the way they show up is sort of tied to the topology of the underlying manifold. So for example, on R2, we know that, or R2n, we know that we can't quantize P squared, basically, or else you get like contradictions. And on the sphere, you also get contradictions, but the weird thing is that on the torus, you don't. So like there's this weird interplay between quantizability, I guess, and the topology of the underlying manifold. I'm just wondering, like, since you're trying to, do the quantization of these, what is it, the observables, the relational observables, and you want to sort of plug in generic scalars into that F, and also you want to have a sort of like a symplectic structure on that. I'm just wondering if you, if anybody actually knows, like how those kinds of obstruction to quantization show up on the moduli space of metrics.
Well, so I mean, on the metrics, I'm not sure if there's an answer to that, but of course, I mean, sure, it's true that that the quantization will very much depend on the underlying topology of your configuration space or even whatever phase space. But in fact, the point you raise about that you get ambiguities when you have polynomials larger than of second order. I mean, that's already something you even have in a flat space. That's this Roeleveld-Van Hove theorem or phenomenon. And so it basically is something where you just have to choose some factor ordering and live with that. So it's really related to the factor ordering ambiguities. But now more generally about the, so this is not anything specific, of course, to gravity, it's just any quantum theory. But now the other issues that you raise, I mean, I think at the level of full GR, I don't think there's any answer to that. So it's just way too complex. But at least in simple models, we have actually discussed it. In fact, well, actually here on the right slides in this paper here with Bianca Dittrich and Mike Nelson, Tim Kozlowski. In fact, we have discussed something like this, topology-dependent quantization of observables, where we basically show that you have to sort of adapt the topology underlying the quantization in the sense in which you're talking about to the observables you want to represent in the quantum theory. And that's something that in simple systems is not really important, but it's in this paper here, what we discuss is sort of semi-integrable model. So semi-integrable in the sense that it doesn't have a full independent set of Dirac observables in the sense of that they actually have differentiability structures. And so then, okay, it's kind of complicated, but at least you can quantize it if you adapt your topology in that case. So that's discussed in this paper here.
Okay, that's interesting. Thank you.
So for the order of the next questions will be Observables, then Steve Giddings, and then I've seen Domenico, Wolfgang, and Guilherme in that order, please.
All right, so thanks first for the very, very nice talk and the great outline you gave and the great overview you gave. I was wondering with this relational quantum observable, is it possible to axiomatize what they actually do? Because they have some nice parameters that are still somewhat tangible. So it seems like a natural question.
Yeah, so that is actually a good question. That's something that hasn't been, so I haven't seen an axiomatization of this in the literature. In fact, it's something that is we're currently working on, but not in the context of gravity, but that's more well, quantum reference systems in quantum information, let's say. So, so it's a bit of a simpler context, and there you can start thinking about what are actually axiomatizations of relational observables, and that goes in line, of course, with trying to axiomatize what you actually mean by a reference system. So, because of course the relational observables are intimately tied with your choice of reference system. So I mentioned at some point some basic properties that these reference systems should have, but of course, you know, what we would like to have in the end is a somewhat more precise axiomatization of this. It's in particular in the spirit of people in quantum information, quantum foundations. They like to think about these objects in a axiomatic way, and so at least for well, finite dimensional phase-based systems, we're currently working on that. But for the full field theory case, yeah, I think that will be hard. So I wouldn't really know how to address that question at this point, other than, you know, just hand wavingly.
All right, still, thank you very much. It's interesting.
Steve, you can ask a question now.
Yes, thank you. And thank you, Philip, for a very nice overview. So maybe a comment / question. This goes back somewhat to what Lee was saying, but I think there's a more important underlying physical issue. We really expect clocks to be built out of physical degrees of freedom somehow, you know, something like quantum fields. And when they are quantum dynamical objects, then we really find that there are limitations on the resolution that you can achieve with them. You know, quantum fields fluctuate and back react and so on. This is one of the things we were driving at in the paper with Merolf and Hartle, and also their 2D toy models in a paper with Gary. So, you know, that really seems to suggest limitations on what you can resolve that look like they could be fundamental limitations on the underlying space-time description. You know, in other words, saying that at the underlying level, we're not dealing with a space-time manifold. And we need to think about a Hilbert space based on some other structure. So I just wanted to point that out and raise the question of how you think about that set of issues.
Yeah, so I mean, so here I guess I'm on the right slide. So so that was what I tried to summarize in one bullet point, what you did in that paper. So of course that's not doing justice to your paper, but yeah, indeed, I mean, I recognize that that is a hard issue, but this is really at first an issue for relating this relational localization to localization in space-time. And yeah, I think the issues that you mentioned there in this effective field theory case, I think there will be fundamental limitations there. Now, if you ask about the relational localization, here I'm not entirely sure. So the reason is that, so one thing that you did in that paper is you sort of considered some of these observables kinematically and then started talking about the fluctuations. But I think there is a qualitative difference when you discuss these objects on the physical Hilbert space, on the space of solutions. And the reason is that in fact, the fluctuations you talk about kinematically, all the fluctuations are sort of independent. So you have to take all of them into account. But on the physical Hilbert space, the degrees of freedom are not all independent. And so the fluctuations of your reference fields, the fluctuations, in the end, they will become the redundant degrees of freedom. And so in a way, the fluctuations of these objects, there are something that you can in principle in these reduction maps, okay, that I didn't really discuss here. I think they will not actually play a decapitating role, at least for relational localization, simply because they are sort of redundant. And you can, in that way, sort of transform them away by putting the fluctuations really into the independent evolving degrees of freedom. So at least you can see that, I mean, of course, in mechanical systems, that's something much simpler. But in principle, you could also ask about fluctuations of, you know, in these relational observables of the clock degrees of freedom. But it just turns out that on the physical Hilbert space, these fluctuations of the clock, they're not really that relevant because you choose these clock degrees of freedom as the redundant ones, and it sort of permits you to sort of transform these fluctuations somewhat away, and then that allows you to construct a sort of symmetry reduced quantum theory where the reference degrees of freedom are no longer quantum mechanical, but are just relegated to parameters. And so I think at least I don't see a fundamental reason why that should not also work, at least in some cases in field theory. In fact, we are working on something like this right now. It's however, a bit too early to say, and it will be a lot more complicated because what you want to do in the end is sort of condition on field configurations. And what you have to do is do that sort of in a Schrödinger quantization of field theory if you want. And so then you have to first of all talk about the whatever configuration space of your fields. And of course, that's a horribly complicated infinite dimensional object. And the quantum states on that, so you have to define them in terms of cylindrical functions and so on. So it's something very complicated, but at least in principle, I don't see that these fluctuations, at least for the relative localization, will be will play a really inhibiting role, at least not when you are in the physical Hilbert space, and that's owing to the redundancy.
Well, I think, if you have a clock that's a scalar field, real scalar fields undergo fluctuations, and in fact, quite violent fluctuations at short distances. So I think that is a real issue, but,
well, no, I mean,
looking at more closely.
No, sure. So I mean, but then when you talk about fluctuations on short distances, then you have the space-time picture in mind. And in that case, I completely agree. When you want to relate that to space-time localization in relative to some space-time manifold in this effective or perturbatively, then I completely agree with you. So there, but I mean, these arguments, you still somehow, you are already assuming that there is some sort of space-time structure in the first place in these arguments here. And in a full non-perturbative quantum theory, this has to come from somewhere. And at least when you don't talk about this, such a sort of classical space-time picture to start in the more fundamental picture, then at least when you talk only about relational localization, and so not localization in that space-time, then I think these conditionings, like in the Page-Wootters thing in principle, at least, I think they will go through. But
Well, I'm just saying that in that approximation, you can see there's.
I'm sorry. I promised 3 more people to ask their questions, and maybe you can continue your discussion on Slack. I know it's interesting, but maybe give other people the chance. I think it was Domenico, then Wolfgang, and then we'll read the last question.
Okay. Yes. Thank you. I have a question about this equation exactly that we see. It's just a minor technical question. I wonder how we should read this. So O of x is supposed to be a local operator, and the delta function is also of a local operator.
Yeah, so here, I mean, that's why I put here in brackets must be regularized. So in this paper, there's a more precise discussion of this that I didn't want to repeat here. So there they replaced this delta function, for instance, with basically a Gaussian.
I thought perhaps it's a delta function on the spectrum. So if you take the spectral resolution of T,
yeah, so I mean,
make a delta function on that.
So I mean, this is this is related to the discussion that I just had with Steve.
Yeah.
So in principle, when you don't, well, okay, I mean, in the space-time picture, I think then I would agree with Steve that it probably becomes problematic to to condition on these readings at particular space-time points due to the fluctuation. So I think there I completely agree with Steve. But at least in this like when you go away from the space-time picture, so what I mean by that, you consider, for instance, a field theory description in a completely diffeomorphism-invariant context where you don't talk about coordinates. So this is in principle possible. What I was talking about before, conditioning on the field states, that would be exactly something like using a spectral resolution of your reference fields and then conditioning on that.
Okay, thanks.
Wolfgang? Wolfgang, are you there to ask your question? So we can't hear you. So I'm reading out Guillermo's question right now. So background independent theories cannot help but to be diffeomorphism-invariant, but the contrary is not true. So diffeomorphism invariance does not imply background independence. In this sense, diffeo invariance, active or not, might not be sufficient to define quantum gravity observables. Any ideas to go beyond if so?
Is Guilherme there to specify this question a bit more? So, so I mean, it's true that, so for instance, you can, of course, I mean, there's this Kretschmann objection to diff invariance playing a fundamental role, where you can basically turn any field theory diffeomorphism-invariant. I don't know if he's referring to that. So you can also do that with a scalar field theory in Minkowski space, and then sure, in that sense, it's not background independent because you have a field theory in Minkowski space. But you do that by introducing either additional degrees of freedom, such as embedding fields, or you're introducing, you have to introduce additional conditions. For instance, when you look at scalar field theory in Minkowski space, the additional conditions could be that, for instance, the Riemann tensor vanishes, so that you're always talking about, Minkowski metric. So there's always additional steps you have to do, and of course, when you just parametrize systems, then you can always artificially introduce symmetries, just like with this parametrized particle that I was discussing. So it is true that diffeomorphism-invariance per se is maybe not the important thing. However, there is a difference in general relativity, because in all these stupid examples, you can always just basically gauge away that diffeomorphism-invariance, and then you don't need to work with that in the first place. But in general relativity, you cannot do that, and that's because the dynamics, I mean, the dynamics is intimately intertwined with the diffeomorphisms, and in general, there's absolutely no way for general relativistic systems to simply deparametrize them globally. It's just impossible. And so in general relativity, generically, that diffeomorphism symmetry does play a fundamental role. It's not something we can simply get rid of. And at least for general relativity, I therefore think that we should definitely take that active diffeomorphism invariance very seriously. But I'm not entirely sure if that answers the question, because I'm not sure I fully understood that question. And so if Guilherme is online, maybe you can ask the question.
In any case, you can also continue the discussion in the Slack. Maybe one last time, give Wolfgang the chance to try and ask his question. If it doesn't work, I will read it out. Okay, so maybe just let me ask the question. Could you explain again why you have to use coherent states, POVMs, rather than eigenfunctions of the clock Hamiltonian?
Well, so I mean, we are, so I guess he's referring to the construction of these clock states. Well, I mean, these, okay, maybe I'm also not completely understanding that question, but of course we are using the eigenstates of the clock Hamiltonian to construct these clock states. And then what we want to do is in the end use these clock states to condition physical states on those, or to define also in the quantum theory what we mean with, what's the value of the observable such and such when the clock reads such and such, because these clock states T here, they correspond then to the different clock readings. That's the interpretation here. So I don't know if Wolfgang meant anything that we should condition instead of on these energy eigenstates of the clock Hamiltonian. I'm not entirely sure. But if he means that, then we should definitely not do it, because that would be, I mean, the clock Hamiltonian in this case is simply a Dirac observable itself. So we would, in that sense, really directly be conditioning on states of an invariant. And so, as I explained before, when you want to have reference systems that are as invariant, as non-invariant as possible, so as asymmetric as possible, in order to provide a resolution of, or to parametrize the orbits. And for that, conditioning on anything of the energy of any of these clock Hamiltonians would just not do the job. And by contrast, these clock states, they are absolutely maximally non-invariant in the sense that they are really, yeah, I mean, they define the simple covariance condition here. So I'm not sure if that answers this question, but Wolfgang, if you're there, maybe you can make more precise if I've missed your point.
Yeah, I think there will also be time in the Slack, which I want to advertise again. Lisa posted the link to the Slack channel in the chat. There you can have more extensive discussions and maybe also references to more literature. But I think we should close the seminar here. And first of all, thank you, Philipp, for this great talk and also for so patiently answering so many questions. And thanks to all of you for joining us today for this first seminar and participating so actively. And at some point we had 180 people in this meeting. It's really great to see. We're really happy. And so thanks again to all of you, and thanks again to Philipp for your great talk.
Thanks to everyone.
Yeah.